Hi everyone. So we're going to take a look today. We're going to continue this idea of derivatives, and we're going to look at the graphs of some derivatives. And I do want to point out that this lesson is technically like much further along in the course sequence, and we'll definitely revisit this, later in Unit 5. But I find it helpful to do just a little bit of this right here when we're first learning about derivatives, because I think having a visual as we move through the next couple of lessons is really helpful. So we learned already that a derivative is just a slope of a tangent line. And so what we have here is this function, and I wish I had printed this in color, but this function that's the solid line, that is this f of x function. And then the dotted line represents the derivative function, okay? And what the derivative function does is tell you the slope of the tangent line to the original function at any x value you choose. So for example, like right here, I can see that this value is 10, right? And that's on the derivative. So that's telling me that if I were to kind of follow this down to this point on the function, the slope of the tangent line at that point would be 10. And as I draw that in, you're probably thinking, that doesn't look like it has a slope of 10. I do just want to point out that the y-axis is numbered very differently than the x-axis is, so this would actually be a much steeper slope. So, but that's what this is telling me, is that whatever numerical value I'm seeing on the derivative graph, that's the slope of the tangent line on the original graph, okay? And so by creating these derivative functions, we can see a lot of relationships that you maybe couldn't see just when you're finding individual derivatives at individual values. I'm going to take this back away just so I can point out the things that I want to. So in class, we do a lot of exploring with this, and we do a lot of, what do you notice, what do you see? That's harder to do in a video, so I'm just going to kind of draw your attention to the things you should notice. And so first of all, the derivative is equal to 0 here, and here, and here. And I want you to think about what that means. A derivative of 0 means a slope of 0, right? And so if I follow those points down to the original graph, or up, as it may be over here that's up, what I see is this is where the graph is changing direction, right? It goes from decreasing to increasing. And so if I were to draw a tangent line in right here, it would be a horizontal line. Anywhere you've got a bump like that, and that's going to happen anywhere you have a maximum or a minimum value, like right here, I would have a horizontal tangent line. And so that point where that horizontal tangent would be, actually it looks like it's moved over just a little bit, but that's representing a 0 derivative. Okay, so anywhere my derivative is equal to 0, what I'm seeing in the original graph is that it's changing direction, that I have a local max or min. So down here, and actually let's see, I'm going to slide this up a little bit so I can see this table down here. The first thing we're going to list is that if the function is changing direction, and by that I mean we have a local, otherwise known as a relative, max or min, then the derivative is equal to 0. Okay, so now let's look at what's happening in between those zeros. So I'm going to start with the kind of middle portion of the graph here. I see that between this 0 and this 0, if I'm looking at this portion of the graph, okay, between those two zeros, or between those two changes in direction, I should say, in that stretch, my graph is increasing. It's always getting larger, right? It's growing, okay? And that means that anywhere in that portion that I kind of highlighted there, if I were to draw the tangent line, the slope would be positive. So what you notice is that on the derivative graph, that entire portion of the derivative graph lives up here above the x-axis, okay? So anytime your derivative is positive, your function is increasing. And we can say that the other way around too. Anytime your function is increasing, you're going to have a derivative that's positive, okay? So if the function is increasing, then your derivative Has to be greater than 0, has to be positive. By the way, missed this, but there's also a 0 here. I didn't draw this tangent line in, that's why I missed it. But if you look, this portion of the graph is also increasing. Okay, as we move to the right, this is constantly growing, and so this portion of the derivative graph is also living above the x-axis. And because this looks like it's going to continue to increase, then this continues to be up above the x-axis. Okay? And so naturally, that kind of leads us to, well, what about when we're decreasing? So like this part of the graph, my function is decreasing. So if I were to draw the tangent lines in anywhere, they would all have a negative slope. And then same thing over here. This little portion of the graph is all decreasing. Okay? And so in that section and all of this, what you'll notice is my derivative is living underground. My derivative is negative. Okay? So if your function is decreasing, then we're expecting our derivative to be negative. There's some more things that we're going to learn about derivative graphs as we go on. Right now, these are the things that would be helpful to recognize. And like I said, as we continue to work with derivatives, just understanding these relationships will be really helpful. Let's try one example where we're going to draw our own derivative here. Okay, so here's a function, x cubed minus 6x squared plus 4x plus 12, and we want to draw what the derivative should look like. Okay, so the first thing I always start with is where are the zeros? I'm seeing a relative max right around here someplace, so I would probably put a 0 here. Okay, that's my derivative 0, right? And then I'm seeing a relative min maybe right here, so I know my derivative is going to have a 0 here. So I know I'm going to cross the x-axis here and I'm going to cross the x-axis here. This portion of the graph up to that 0, all of this is increasing. So I'm going to expect my derivative to live up here in positive territory. Okay, I'm just kind of sketching some things right now. And then from here to here, my graph is decreasing. Okay, and so in this area of the graph between my two dots here, I'm expecting my graph to live down here, my derivative graph. And then all of this is increasing, so once again, I'm expecting this portion of the graph to live up above the x-axis again. It's positive. Okay, so we need a graph that is positive and then negative and then positive, and it crosses here and here. And so I am guessing this looks something like this. Okay. Now, don't stress about it right now. If you're not sure, like, how low should I make this go, or how wide should I make this? We're not getting anything real numerical here. Really, these relationships are what I'm expecting to see. Do you know where the zeros should be? Do you know where you should be positive? Do you know where you should be negative? Okay. One interesting observation that came up when I taught this most recently is somebody pointed out, well, hey, that's x cubed. And when I took my derivative, my graph looks like an x squared function. That's absolutely an accurate observation, that the derivative is always going to be one smaller in terms of degree than what the original function is. And we're going to learn the reasoning for that later on, but that's definitely a thing. I'm glad you're noticing that. If you look back at this one we did originally, my original function was a degree 4. It went down and then up and then down and then up again, okay, degree 4. My derivative is a cubic function. Okay, so that is definitely a relationship that you're going to see and revisit again.